Now we move to the final technical section of the lecture, the role of geophysics in CCS. This is especially important today because geophysical methods are no longer used only for finding hydrocarbons. They are now essential for safely monitoring underground carbon storage. Norway is one of the leading countries in offshore CO2 storage, and this slide shows the scale of that effort. The maps highlight potential and active storage areas and demonstrate how regional subsurface understanding is needed before any project begins. Geophysics plays a major role here because it helps define storage formations, seal integrity, and basin scale structure. This slide shows an example from the Northern Lights context, where simulation grids, reservoir property cubes, and elastic parameters such as acoustic impedance and Vp/versus are combined. One very important point here is that the effect of injected CO2 on these seismic parameters can be subtle. That means monitoring is not always straightforward, and careful integration of rock physics, geophysics, and modeling is required. Here we see how geophysical and simulation-informed analysis can track CO2 plume evolution over multiple years. The plume does not remain fixed. It migrates according to the reservoir geometry, buoyancy, and structural dip. This is a very important concept in CCS because safe storage depends not only on where CO2 is injected today, but also on where it may move in the future. Time-lapse seismic, also called 4D seismic, compares repeated seismic surveys acquired at different times. By subtracting or comparing surveys, we can detect changes associated with CO2 injection and plume migration. This is one of the most powerful monitoring tools in CCS because it gives a spatially extensive picture of reservoir change over time. This example from Canada shows how seismic sections are used to support geomodel construction. The seismic image helps identify stratigraphic boundaries and structural continuity across the storage interval. In practical terms, this means geophysics helps transform regional geological understanding into a structured 3D model that can be used for simulation, capacity estimation, and risk analysis. This slide continues the Canadian example by showing a detailed geomodel illustrating effective porosity from seismic data, along with CO2 saturation after 1 year, 5 years, and post-closure periods. The key message is that geophysics can contribute not only to imaging structure, but also to supporting spatial property models and understanding saturation evolution over time. This slide introduces the Ketzen pilot storage site in Germany and shows both regional location and interpreted depth to the top Stuttgart formation, along with mapped faults. This is a classic example of how 3D seismic supports pilot-scale CCS monitoring by defining the structural context, reservoir horizon, and fault framework around the storage site. This slide shows normalized amplitude differences between baseline and repeat seismic surveys at the reservoir level for multiple years. The white dot marks the injection well, and the amplitude differences show how the monitored response evolves over time. This is an excellent example of geophysics used not just once before injection, but repeatedly during storage operations to monitor dynamic changes. This slide summarizes three major roles of seismic surveys in carbon storage. First, they can track CO2 migration and confirm that the plume stays within the intended area. Second, they can help detect leakage pathways, such as faults or fractures. Third, they support reservoir management by monitoring structure and stability over long periods. This slide is one of the most important take-home messages of the CCS section.